In this video, I am going to make a video for visual impaired student. Metal ligand bonding in transition metal complexes. Transition metals have very good tendency to form coordination compounds or complexes, though many attempts were made by different workers to explain the bonding and structure of coordination compounds. The main credit goes to the brilliant work of Werner. In 1893, Werner proposed a theory which is commonly known as Werner's coordination theory. This was the first successful attempt to explain the bonding in coordination complexes. In recognition of his work in this field, Werner was awarded Nobel Prize in 1913. He explained the bonding in these complexes on the basis of two types of valences of the metal: the primary valency corresponding to oxidation state and the secondary valency corresponding to coordination number. The secondary valency or coordination number determined the stereochemistry of the complexes. However, the Werner's assumptions were not based on theoretical justification, and the scientists started making attempts to find bases of bonding in these complexes. The first attempt in this regard was made by Sidgwick, who extended the Lewis theory of electron pair bond formation to explain the bonding in transition metal complexes. He suggested that the metal ion atom accepts electron pair from ligands until it achieves the next noble gas configuration and gave a term effective atomic number. Effective atomic number is the total number of electrons possessed by the central metal ion and the electrons gained by it from ligands. However, this theory lacked fundamental basis and simply gave emphasis on the stability of inert gas configuration in coordination compounds. With the advances in theories of chemical bonding, three modern theories of bonding in transition metal complexes have been developed. These are valence bond theory, crystal field theory, molecular orbital theory. In the present text, we shall discuss mainly crystal field theory of bonding. The valence bond theory has already been discussed in the previous classes. Valence bond theory was developed by Linus Pauling and assumes the bonding between the metal atom or ion and the ligands to be purely covalent. It presents a simple description of metal ligand bonding using hybrid orbitals of the metal and the electron pair of the ligands. The basis of VBT is that the appropriate vacant atomic orbitals sp and d of the metal atom hybridize to give a set of hybrid orbitals which are directed towards the ligands according to definite geometry of the complex. The bonding in metal complexes arise when a filled orbital of the ligand containing a pair of electrons overlap with a vacant hybrid orbital on the metal atom ion, forming a covalent sigma bond called coordinate bond. In addition to a sigma bond, there is also a possibility of pi bond provided suitable orbitals are available on the metal atom and the ligands. The total number of metal atomic orbitals which undergo hybridization is equal to the coordination number of the central metal atom or ion. For example, for coordination number 6 complexes D 2d, 1s and 3p orbitals, that is a total of 6 orbitals of the metal atom, are involved in hybridization. The d orbital involved in the hybridization may be either inner n-1 d orbitals or outer n d orbitals, giving inner orbitals or outer orbital complexes. For example, in case of octahedral hybridizations, the orbitals may be 1 ns, 3 np and 2 nd sp3d2 hybridization, or 1 ns, 3 np, 2 n-1 d d2 sp3 hybridization. Similarly, for coordination number 4 complexes, tetrahedral structure can be considered to arise from bonding with 4 sp3 hybrid orbitals formed by the coordination of 1 ns and 3 np atomic orbitals or square planar structure. arising from bonding with the 4dsp2 hybrid orbital using n-1d, ns, n2, np, npx and npy atomic orbitals. Some common type of hybridization of atomic orbital and their geometries are given in table. For coordination number 2, hybridization is sp and shape is linear. For coordination number 3, hybridization is sp2 and shape is trigonal planar. For coordination number 4, hybridization is sp3 and shape is tetrahedral. And also the hybridization is dsp2 and square planar if d orbital involved is dx square y square of the inner, that is n-1 shell. For coordination number 5, the hybridization is dsp3. The d orbital involved is dz square of the inner, that is n-1 shell, and the shape is trigonal bipyramidal. And the hybridization is also sp3d. The d orbital involved is dx square y square of the outer, that is the nth shell, and the shape is square pyramidal. For coordination number 6, d2sp3 or sp3d2, the d orbital involved are dz square and dx square y square of the inner, that is n-1th shell in the first case, and of the outer, that is nth shell in the second case, and the shape is octahedral. Now the limitation of VBT. The valence bond theory successfully explained many stereochemical and magnetic properties of coordination compound. However, it has many limitations. The main limitations of VBT are: it provided only qualitative explanation for complexes. Second, it does not explain the color and electronic spectra of the complexes. Third, the theory fails to explain why some metal complexes in a particular oxidation state are low spin complexes, while some other complexes of the same metal ion in the same oxidation state are high spin complexes. For example, in the complexes CO NH36 and the oxidation state 3 positive, COF6 3 negative, the oxidation state of cobalt is +3. But the former is low spin inner orbital complex and the latter is high spin outer orbital complex. It does not predict the relative stabilities of different complexes. We know that certain complexes are labial, in which the displacement of ligand takes place repeatedly, while some are inert, in which ligand displacement by another ligand is very slow. VPT does not explain the kinetic inertness of complexes such as chromium 3 and low spin cobalt 3 octahedral 3 complexes. It does not explain the variation of magnetic moment values with temperature. It does not take into account the splitting of d energy level. It does not predict the relative stabilities of different structure. The VBT does not predict whether the 4-coordinate complex will be square planar or tetrahedral. This can be explained only on the basis of magnetic moment values of the complex. For example, the decision about the geometry of nickel 2 complexes depend upon the magnetic moment values. For example, nickel 2 ion has the electronic configuration 3D. If the complex involves sp3d hybridization, it would have tetrahedral structure. For the formation of tetrahedral structure, the 3D orbitals remain unaffected and the complex is paramagnetic. On the octahedral, if the complex involves dsp2 hybridization, it would have square planar structure. This is possible if the two unpaired d electrons are paired up, thereby making one of the 3D orbital empty. This is there. Thus, no unpaired electron and the complex would be diamagnetic. It also fails to give a satisfactory explanation for the formation of square planar tetraamine copper ion. The valence bond theory does not tell us why water and halide ion commonly form high spin complexes, cyanide ion form low spin complexes. To answer some of the above problems, let us discuss other theories. Crystal field theory, CFT. The CFT was developed by H. Bethe and V. Black. This theory is based on entirely different assumptions than the VBT. As we have already learned, the VBT considers the bonding between the metal ion and the ligand as a purely covalent. On the other hand, the CFT considers the bond between metal ion and the ligand as a purely electrostatic. This theory is based on the assumption that the metal ion and the ligands act as point charges and the interaction between them are purely electrostatic. In case of negative ligands, anions such as Cl negative, Br negative, Cn negative, the interaction with metal ions are ion-ion interactions. If the ligand are neutral molecules such as NH3H2O, the interaction with the metal ions are ion-dipole interaction. For example, in the case of complex ion, the interactions are between CO3 positive and F negative ions, whereas in CONH3 positive, the interactions are between negatively charged end of NH3 molecules, delta charge on N atom, and CO3 positive ion. The central idea of this theory is that the electrons of the metal ion in the environment of other ions or molecules, as for example within the lattice of a crystal, are affected by a non-spherical electrical field established by the surrounding ions or molecules. The electric field was called the crystalline field, but now it is called as crystal field. This is responsible for the name crystal field theory. Basis of crystal field theory. The basic assumption of crystal field theory are: the transition metal ion is surrounded by the ligand with the lone pair of electrons. All types of ligands are regarded as point charges. The ligands may be either ionic or molecules. If the ligand is a neutral molecule, then the negative end of the dipole is oriented towards the metal ion. For example, ammonia is polar molecule have delta negative charge on N and delta positive charge on hydrogen atom. Similarly, water is also positive with delta negative charge on oxygen atom and the delta positive charge on hydrogen atoms. Third, the interaction between the metal ion and the negative ends of anions is purely electrostatic. That is, the bond between the metal and the ligand is considered 100% ionic. Fourth, the ligand surrounding the metal ion produce electrical field, and the electrical field influences the energy of the orbitals of the central metal ion, particularly d orbital. In the case of free metal ion, all the 5d orbitals have the same energy. These orbitals having the same energy are called degenerate orbitals. This means that an electron can occupy only one of these 5d orbitals with equal ease. However, on the approach of the ligand, the orbital electrons will be repelled by the lone pair of the ligands. The repulsion will raise the energy of the d orbital. If all the ligand approaches the central metal ions are at equal distance from each of the d orbitals, the energy of each d orbital will increase by the same amount. Therefore, these orbitals will still remain degenerate, but they will have higher energy than before. But we know that d orbitals have different orientation, and therefore these orbitals will experience different interactions from the ligand. The orbitals lying in the direction of the ligands will experience greater repulsion and their energy will be raised to greater extent. On the other hand, the orbitals lying away from the approach of the ligand will have lesser interaction, and therefore their energy will be raised to lesser extent. Therefore, due to electrical field of the ligands, the energy of the 5d orbital will split up. The conversion of 5 degenerate d orbital of the metal ion into different sets of orbitals having different energies in the presence of electrical field of ligands is called crystal field splitting. This concept formed the basis of crystal field theory. 6. The number of ligand, coordination number, and the arrangement around the central metal ion will have different effect on the relative energies of the 5d orbitals. In other words, the crystal field splitting will be different in different structure with different coordination numbers. 7th, the magnetic properties, spectra, and preference for particular geometry can be explained in terms of splitting of d orbital in different crystal fields. Thus, to understand the crystal field theory, it is essential to have a clear picture of the disposition of the 5d orbital in space and the geometrical arrangement of the ligands around the central metal ion. We may illustrate this concept by considering the complexes with coordination number 6 and 4, which are very common. Shapes of d orbitals. There are 5 d orbitals. These are designated as dxy, dyz, dzx, and d square, dx square, y square, and dz square. The shapes of these orbitals are described below. The three orbitals dxy, dyz, and dzx are similar and each consists of four lobes of high electron density lie in xy, yz, and zx plane respectively. These lobes lie in between the principal axes. For example, in case of dxy orbitals, the four lobes lie in xy plane in between the x and y axes. The dx square y square orbital has also four lobes of high electron density along the principal axes x and y. It may be noted that this orbital is exactly like dxy orbital except that it is rotated through 45 degrees around the z-axis. Third, the dz square orbital consists of two lobes along the z-axis with a ring of high electron density in the xy plane. It may be noted that although dz square, dxy square orbital do not look to be similar, yet they are equivalent so far as interaction with the metal ions are concerned. The dx square orbital can be regarded as a linear combination of two orbitals, dz square x square and dz square y square, each of which is equivalent to the dx square minus y square orbital as shown below. However, it may be noted that these two orbitals dz square x square and dz square minus y square do not have independent existence, but the dz square orbital can be thought of as having the average property of the two. Since both the orbital dz square x square and dz square y square have high electron density along the z-axis, therefore, dz square orbital has a large fraction of electron density concentrated along z-axis. Moreover, one of the component orbital dz square x minus x square has lobes along the x-axis and the other dz square minus y square has lobes along the y-axis. The resultant d orbital has electron density in xy plane shown as donut ring or a column. Crystal field splitting in octahedral complexes. In an octahedral complexes, coordination number 6, the metal ion is at the center of the octahedron and the ligand are at the 6 corners. The three axes are x, y, and z point along the corners of the octahedrons and are also shown. Let us suppose that the metal ion Mn positive has a single d electron. In the free ion, when there are no ligands, the electron can occupy any one of the 5d orbitals because all are of the same energy and are called degenerate orbitals. However, in the octahedral complex mx6, all the 5d orbitals will not remain of equal energy. This can be easily understood by considering the shape of this orbital in the octahedral field of the ligands. The comparison of arrangement of d orbital in figure 4 shows that the two lobes of dx square and the four lobes of dx square minus y square orbitals point directly towards the corner of the octahedron, whereas the negative charge of the ligands are concentrated. The remaining three orbitals are oriented in between the axes. In the case of octahedral complexes, the former two orbitals are designated as Eg, pronounced as Eg orbital, while the later three orbitals are designated as T2G orbitals. As the two ligands approach the central ion along the axis, the Eg orbitals are repelled more than the T2G orbitals. In other words, energy of the dz square and dx square minus y square orbital increases much more than the energy of the dxy, dyz, and dzx orbitals. It should be remembered that when a charge is repelled by a similar charge, its potential energy increases. The greater the repulsion, the greater is the increase in energy. Thus, in octahedral complexes, the 5d orbitals split up into two sets. One set consisting of two orbitals of high energy Eg orbitals and the other set consisting of three orbitals of lower energy. The phenomena of crystal field splitting in an octahedral complex is this. The energy difference between two sets of d orbital T2G and Eg is called crystal field splitting energy and is symbolically represented as triangle node. The subscript stands for octahedral. The magnitude of triangle knot varies for different complexes. The crystal field splitting is also measured in terms of another parameter called dq. The two are related as delta knot is equal to 10 dq. There are two parameters are very commonly used. It may be noted that the crystal field splitting occurs in such a way that the average energy of the d orbitals does not change. This is known as barycenter rule, which is similar to center of gravity type rule. This means that the decrease in energy of the set of orbitals that lie at the lower energy level must be balanced by the corresponding energy in another set. Therefore, in terms of total energy 10 dq, the energy of each of the two Eg orbitals is raised by 6 dq and the energy of each of the three T2g orbitals is lowered by 4 dq. In terms of delta knot, the energy of each of the two Eg orbitals is raised by 3 by 5 delta knot or 0.6 delta knot, and the energy of each of three T2g orbitals is lowered by 2 by 5 del knot or 0.4 del knot. The value of 10 dq or del knot measured spectroscopically. In figure 5, we observe that initially the energy of all the 5d orbitals are raised equally as shown in state 2. This would be observed if the field created by the ligands was spherically symmetrical. However, the energy of d orbitals split into two steps because of the different orientation of the orbitals towards the ligand as shown in state 3. Crystal field stabilization energy. We have learned that in an octahedral field, the energy of 5 d orbitals split up. 3 orbitals are lowered in energy T2g and 2 orbitals are raised in energy Eg. We note that the electrons will always prefer to occupy an orbital of lower energy. For example, in the case of d1 system, the d electron will prefer to occupy a T2g orbital and is therefore stabilized by an amount of equal to 0.5 for del knot or for dq. The amount of stabilization provided by splitting of the d orbitals into two levels is called crystal field stabilization energy. It is abbreviated as CFSE. Thus, in octahedral field, for each electron entering into the T2g orbitals, the crystal field stabilization is minus 4 dq, and for each electron entering into the Eg orbitals, the crystal field stabilization energy is plus dq. Thus, the CFSE is calculated as the algebraic sum of minus 4 dq per electron in T2g level and plus 6 dq for each electron in Eg orbital. CFSE for various octahedral complexes. For a d1 system, electron will be present in any one of the three T2g orbitals. The electronic configuration may be written as T2g1 and the crystal field stabilization energy is minus 4 dq. For a d2 system, the electrons will occupy T2g orbitals with their spin parallel in accordance with Hund's rule. The electron configuration is T2g2 and the crystal field stabilization energy is minus 8 dq. Similarly, for a D3 system, the electronic configuration is T2G3. The crystal field stabilization energy is minus 12 dq. For a D4 system, there are two possibilities. All the four electrons may occupy T2G orbital with one electrons get paired. The electronic configuration may be written as T2G4. Three electrons occupy T2G orbitals and the fourth electron goes to one of the Eg orbitals. The configuration may be represented as T2G3 Eg1. The actual configuration may be decided on the basis of delta knot and the pairing energy P, that is the energy required to pair the electrons with one another. The configuration A is possible if del knot is greater than pairing energy. These complexes are stronger field complexes because del knot is large. In this case, the complex ion has less number of unpaired electrons and is called low spin complex. The configuration B is possible if del knot is less than pairing energy. It is called weak field and the complexes are called weak field complexes. In that case, the maximum number of electrons remain unpaired and the complex is called high spin complex. As shown above, for a low spin complex having T2G configuration, CFSC is equal to minus 16 dq. However, if we take into account pairing energy, also the net CFSC becomes minus 16 dq plus p. On the other hand, for high spin complexes having the configuration T2G3 EG1, CFSC is equal to 3 minus 4 dq plus 1 6 dq is equal to minus 6 dq. Fifth, for a d5 system, there are two possibilities. While the 5 electrons may occupy T2G orbitals with the two orbitals get paired up, the electronic configuration may be written as T2G5. This is possible if delta naught is greater than P, and the complex will be called strong field or a low spin complex. The 3 electrons occupy T2G orbital and the 2 electrons occupy EG orbitals. The electronic configuration may be written as T2G3 and E2G. This will be possible if delta naught is less than P and the complex is called weak field or high spin complex. The CFSC in these two types of complexes will be strong field if delta naught is greater than P. Then CFSC is equal to minus 20 dq plus 2p. For weak field, if pairing energy is greater than del naught, CFSC is equal to 0. Similarly, D6 and D7 systems have two possibilities depending upon the relative magnitude of crystal field splitting energy and the pairing energy of the electron. For a D6 system, example CO3 positive ion, strong field is equal to del naught greater than P, CFSC is equal to minus 24 dq plus 2p. For weak field ligand, if pairing energy is greater than del naught, CFSC is equal to minus 4 dq. For a D7 system, CO2 positive ion, strong field when del naught is greater than P, CFSC is equal to minus 18 dq plus P. For a weak field when pairing energy is greater than del naught, CFSC is equal to minus 8 dq. The D8, D9 and D10 systems have only one possible configuration. This is because if we assume the complex to be high spin, the first 5 electrons would go 1 each into 5d orbitals, and the low spin, the first 6 electrons would fill the T2G orbitals and the remaining 2, 3 or 4 electrons would go into the T2G orbitals. In both cases, the configuration will be the same. Therefore, there is only one possible electronic configuration for D8, D9 and D10 system. For a D8 system, example Ni2 positive ion, CFSC is equal to minus 12 dq. For a D9 system, CFSC is equal to minus 6 dq. For a D10 system, CFSC is equal to 0. The d electron configuration for a weak field and a strong field of octahedral symmetry are given. The crystal field stabilization energy for metal ions having different configuration are summed up. It may be noted that for the strong fields, the electrons always pair up in the lower level first, T2G, filling it before entering the higher level, e.g. for weak field, each orbital, whether of high or a low energy, receives one electron each before any pairing starts. Therefore, weak field configuration always have the same pairing scheme as the free ion. Crystal field splitting in tetrahedral complexes. The coordination number for tetrahedral complexes is 4. The tetrahedral arrangement of 4 ligands surrounding a metal ion may be visualized by placing ligands on the 4 of the 8 corners of a cube. The direction x, y and z point to the center of the faces of the cube. It is clear that the orbitals dxy, dyz and dzx point between xy and z axis, whereas the orbital dx square minus y square and dz square point along x, y and z axis. It is clear that in tetrahedral field, none of the d orbitals point exactly towards the ligand, and therefore the splitting of energy will be less than that in octahedral field. The 3d orbital dxy, dyz and dzx are pointing close to the direction in which the ligands are approaching, while the 2 orbital dx square minus y square and dz square are lying in between the ligands. Therefore, the energy of the three orbitals will be raised while the energy of the two orbitals will be lower. In the presence of tetrahedral field, the degeneracy of 5d orbitals split up as the two orbital dx square minus y square and dz square become stable and their energies are lower. These are designated as E orbitals. The three orbital dxy, dyz and dzx become stable and their energies are raised. These are designated as T2g orbitals. The magnitude of crystal field splitting energy is the difference between E and T2 orbital is designated as a delta T. It is also measured in terms of dq and delta T is equal to 10 dq. If we compare the magnitude of crystal field splitting in octahedral and tetrahedral complexes having same metal ions ligand and metal ion ligand distances, it has been observed that the crystal field splitting in tetrahedral complexes is considerably less than in octahedral complexes. It has been found to be delta T is equal to 4 by 9 del no. Reasons for the smaller value of crystal field splitting in tetrahedral than in octahedral complexes. There are two main reasons for this. In tetrahedral complexes, there are 4 ligands while there are 6 ligands in octahedral complexes. Therefore, lesser ligands produce less crystal field splitting. The crystal field splitting in tetrahedral field is about two-thirds of the octahedral field. In tetrahedral field, none of the orbitals is pointing directly towards the ligands and therefore splitting is less. Since the magnitude of crystal field splitting in tetrahedral field is quite small and is always less than the pairing energy, therefore the pairing of electron will never be energetically favorable. Thus all the tetrahedral complexes are high spin complex. No tetrahedral complex with low spin has found to exist. CFSC for tetrahedral complexes. As we know that an electron always prefers to occupy an orbital of lower energy. Since average energy of the d orbitals does not change, barycenter rule, therefore in terms of n dq, the energy of each of the e orbitals is lowered by 6 dq and the energy of each of the t2 orbital is raised by 4 dq. CFSE is therefore calculated as the algebraic sum of minus 6 dq per electron in e orbital and plus 4 dq for each electron in t2 orbitals. In terms of delta T, the energy of each e orbitals is lowered by 3 by 5 del T, while each of the t2 orbitals is raised by 2 by 5 del T. For example, for d1 system, the electronic configuration is E1. Therefore, CFSC is equal to minus 60 Q. For D2 system, the electronic configuration is E2. Therefore, CFSC is equal to minus 12 dq. For D3 system, the electronic configuration is E2 T12. As already discussed, crystal field splitting in tetrahedral field is quite small and is always less than the pairing energy. Therefore, pairing does not occur and most of the complexes are high spin complexes. Therefore, the CFSC for complexes with metal ions having different configuration of d orbital in tetrahedral fields are given in table. Crystal field splitting in tetrahedral and square planar complexes. The splitting of d orbital in tetragonal and square planar complexes can be easily understood from the non-splitting of d orbital in octahedral complexes. This is because tetragonal and square planar geometries can be understood by withdrawing two trans ligands from an octahedral complex. This process is called elongation. Generally, we consider the removal of trans ligands along the z-axis. As the ligands lying on the z-axis are moved away, the ligands in the xy plane tend to approach the central ions more closely. As a result of increase in metal-ligand bond along z-axis, the repulsion from the ligands to electrons in dz square orbital decreases and therefore the energy of dz square orbital is decreased relatively to that in octahedral field. At the same time, the metal ligand bond along x and y are shortened so that the d orbital in xy plane dx square minus y square experiences greater repulsion from the ligand and therefore its energy is raised. Similarly, the dxz and dyz orbitals are lowered in energy because of decrease in repulsion effects along the z-axis, while the energy of dxy orbital is raised. The resulting splitting pattern is shown in figure. This state represents tetragonally distorted octahedral structure, as the transligands lying along z-axis are completely removed. A square planar complex is formed. In the square planar complex, there is a further rise in the energy of dx2 minus y square and dxy orbitals, and a further fall in the energies of the dz square, dxz and dyz orbitals. It has been observed that in a square planar complex, the energy of dz square orbitals falls even below, and the dxy orbitals. The change of an octahedral complex to the tetragonally distorted octahedrals, and finally to square planar arrangement. It may be remembered that tetragonally distorted structure can also be obtained when the two transligands are brought closer to the metal ion. This is called flattening of an octahedron. This is shown elongation of octahedron. In flattening of octahedron, the two trans metal ligand bonds are shortened, while other four metal ligand bonds become large. The splitting of energies of d orbital will be reverse of what has been observed in the case of elongation. Factors determining the magnitude of crystal field splitting. The following factors influence the magnitude of crystal field splitting. First, nature of the ligand, spectrochemical series. The crystal field theory depends upon the nature of the ligands. The greater the ease with which the ligands can approach the metal ions, the greater will be the crystalline field splitting caused by it. The ligands which cause only a small degree of crystal field splitting are called weak field ligands, while those which cause a large splitting are called strong field ligands. The spectrochemical series is an experimentally determined series. It is very difficult to explain the order because it incorporates the effects of both sigma and pi bonding. In general, the variations in the splitting is caused by a number of factors such as small ligands can cause greater crystal field splitting because they can approach the metal ion closely. For example, F negative ion produces more delta knot value than large chlorine negative and bromine negative ions. The ligands containing easily polarizable electron pair will be drawn more closely to the metal ion. The ligands which have great tendency to form multiple bonds such as cyanide negative and NO2 negative cause greater crystal field splitting. The very high crystal field splitting produced by Cn negative ligands, about double that for weak field ligands like halide ions. This is attributed to the pi bonding in metals. The metal donates electrons from a filled T2g orbitals into the vacant orbitals on the ligands. The following patterns of increasing sigma donation is observed. Halide donors is less than oxygen donors, which is less than nitrogen donors, and which is less than carbon donors. The common ligands can be arranged in an increasing order of crystal field splitting. The regular order is called spectrochemical series. The order remains almost same for different metal ions. The spectrochemical series in the increasing order of crystal field splitting is given below. From the series, it is clear that CO, Cn negative and NO2 negative are strong field ligands, whereas I negative, bromine negative and chlorine negative are weak field ligands. Oxidation state of the metal ions. The magnitude of the crystal field splitting depends upon the oxidation state of the transition metal ion. The metal ion with higher oxidation state causes larger crystal field splitting than is done by the ions with the lower oxidation state. For example, the crystal field splitting energy del naught for complex in which the oxidation state of cobalt is +3 is 18600 cm square, whereas for the complex COH262 positive in which the oxidation state of cobalt is +2, delta naught is equal to 9300 cm inverse. Similarly, for the values of delta naught are 13700 cm inverse and 10400 cm inverse respectively. This is clear from the following data, in which the crystal field splitting energy for hexa-aqua complexes of N2 positive and Mn3 positive ions are given. Types of d orbitals transition series. The extent of crystal field splitting for similar complexes of a metal in the same oxidation state increased by about 30 to 50% on going from 3D series to 4D series. The increase is almost the same amount on going from 4D series to 5D series. This may be explained on the basis that 4D orbitals in comparison to 3D orbitals are bigger in size and extended farther into space. As a result, the 4D orbitals can interact more strongly with the ligands, and therefore the crystal field splitting is more. Similarly, 5D orbitals are bigger than 4D orbitals, and delta knot for the third transition series is more than that for the second transition series. This is evident. Geometry of the complex. As mentioned earlier, the crystal field splitting energy of tetrahedral complexes is nearly half the value of delta knot for octahedral complexes, that is, del T is nearly 4 by 9 times of delta knot. In other words, the value of splitting energy of tetrahedral complexes in general is small as compared to the pairing energy P. The tetrahedral complexes are therefore mostly high spin complexes. Thank you. Thank you for watching.